Hello, scholars. Welcome back. I'm really excited to go through this set of future value equations. For some reason, when I was learning finance, I always loved these. And I think the reason is, as an undergrad, I always thought of what are savings worth? What could they be? And also this idea of perhaps that one day I'll be a millionaire. So let's take a look. These are a really cool set of formulas. Before we start diving with the numbers, I just want to show you back what we're doing is we're going to go and do one of each equation, one of each example, all these future value tools, starting with the future value ones. So again, there probably should be a sigma on that one. We're going to start with uneven cash flows, move into annuities, both ordinary and then annuity dues, and then look at growing annuities. All right, so the first one are uneven cash flow. So with uneven cash flows, the most important thing here is just to try to visualize these as a timeline. Often students will get the time off by 1 year. So if this is time 0, t equals 0, that's my notation for today. At time 1, you're going to receive $200. So that's our year 1 cash flow. At time 2, say you're going to receive $400. Notice how I like to do examples of me receiving money. At time 3, if I receive 600, and then at time 4, that's 800. So as you do practice, you may not need to write all these out, but for now we will. What is the value of the following cash flows in year 4 or 4 years from today? So that's the question. Notice this first one at time 4. That one's already given at time 4. So the first cash flow we get in 1 year actually gets to compound once, twice, 3 times. It does not compound 4 times because you receive it in 1 year, so it only compounds 3 times. So again, you're receiving it in 1 year. If this is today, there's no cash flow occurring today. In 1 year, you receive 200, you're able to compound it once, twice, 3 times up until time 4. So most students first time they learn that will maybe think that that is actually 4 times, but that first cash flow only gets to compound 3 times. So if you're going to do this using the formula approach, the cash flow value at time 4 of that cash flow received at time 1 is going to be 1 plus r to the power of 3. The second one, the cash flow received in year 2, is going to compound twice. So its future value is 400 times 1 with r to the power of 2. And then again, year 3, that's going to compound once. And then the fourth cash flow, there's no need to compound that. It's already given at that time. That's the same as 1 plus r to the 0, and that term would just be 1. So it would just be 800. The other way you could do this in your financial calculator is say, well, I'm just going to calculate their present value. So you could value these as uneven cash flows, determine what they're all worth today as one lump sum, and then compound that value for periods. That's probably the most straightforward, fastest way to do it. So on your financial calculator, what I like to do, cash flow, there's numbers in there already. So then second, clear work, that'll zero everything out. There's no cash flow today. So cash flow at time 0 is 0. Scroll down, that first cash flow is 200. Scroll down, the frequency is 1. You get that cash flow only 1 time. Cash flow 2 is 400. Scroll down, that frequency is 1. Cash flow 3 is 600. Enter, and then down, that frequency is 1. And then the fourth cash flow is 800. Enter, and then compute your net present value at a discount rate of 12.12%. Enter, down, compute. So the present value of these cash flows, which you may have remembered from a previous example, came to 1432.93 today. That's what they're worth right now. So I'm going to then put this in as my present value. I'm treating this as a single cash flow. That's your present value with no payments in between now and then over a 4-year period at a compound rate of 12%. and then I'm going to compute my future value. That's going to come out negative. That's just the direction that way you could think of it as your financial calculator saying, how much would you need to invest today to receive an amount in the future? But the correct answer is 2,254.75. So again, that was just a two-step process using cash flows and then using this five-step button here with NIYPV, payment and future value. So now the next question is a little bit trickier. We have a few things going on, and this one is very, very helpful to think of as a timeline. So I'm just going to draw these out on a timeline. If that's time zero, we know all of these cash flows today are going to be worth $8,600. We were given the first cash flow of 2,200. We don't know the second cash flow. We'll just call that X for now. Cash flow 3 is 2,800. And then the fourth cash flow is $3,400. So the first step here to find the value of the missing cash flow, what I'm going to do is actually figure out the contribution of the 3 cash flows I'm given and then deduct that from the total present value. So another way to think of this is if I were to discount all 4 of these cash flows, if I knew all their values and I discounted them, they're all worth $8,600 today. However, we don't know one of the cash flows. So we have to discount the cash flows we're given, which is the first cash flow, the third cash flow, and the fourth cash flow. So if I discount these, I know how much they contribute to the present value of 8,600. So I'll just put PV of 1, 3, 4 right here. And if I subtract their present values from the 8,600, so I do 8,600 minus whatever the present value of cash flow 1, 3, and 4 is, I'll be left with the present value of the second cash flow, CF2. That's the value of the missing cash flow today. To then find its value, we need to compound it 2 periods. So it's a 2-step process, and let's go through it. So I'm going to go cash flow because this is an uneven cash flow valuation technique, and I'm only going to value the first cash flow at time 1, the third cash flow, and the fourth cash flow. So cash flow 0, we're going to leave in at 0. Enter down the first, cash flow, second, clear work, that should zero everything out. So cash flow 0 is 0. Scroll down to cash flow 1, that's $2,200. Enter. Scroll down, it has a frequency of 1 time. And the second cash flow, we don't know that yet, so we're just going to put in a 0 for there. So it'll have 0 contribution in a frequency of 1. The third cash flow is $2,800. Enter, and that'll have a frequency of 1. And the fourth cash flow is $3,400. And it will have a frequency of 1. So all we have in the cash flows is cash flow 1, cash flow 3, and cash flow 4. So now when I compute that net present value at a 9.4 discount rate, enter down, and then compute, they're worth 6,523. That's the present value of 1, 3, and 4. So I'm going to just erase these and say those 3 cash flows are worth 6523.06. So if I subtract that from the 8,600, that result becomes the present value of the second cash flow. So that's $2,076.94. So all I need to do is compound this cash flow, since it's the present value, and discount it 2 periods. And then I know its value at time 2. So, and that was there's the 2,076. That's your present value. Let's just save that to get rid of the NPV there. Okay, so that's your present value. We should think of that as a negative figure. with no payments over 2 periods at a discount rate of 9.4. And we'll compute that present value, that future value. That's 2485 we think is the missing value of X. And I say think because we're going to just double check our work here. 2485.75. So one way you could check this is to just save this number, store 1, go back to your cash flows and recall that you put in a 0 for cash flow 0. And we're going to scroll down to cash flow 2, recall that number, enter it in there as cash flow 2. So now we have cash flow 0 is 0, cash flow 1 is 22, cash flow 2 is 2485, cash flow 3 is 2800, and then cash flow 4 is 3400. So when we compute this NPV, what do you think we should expect? Wait a second to think about that. We should actually get the 8600, which is the present value of all 4 of those. So we did check out that this is the correct value for the cash flow at time 2. So that's a very tricky one. It involves uneven cash flows. First step was their present values of several of them, and then determining a future value. So that's a really, really interesting question. Probably one of the hardest uneven cash flows you'll ever see. So now find the future value of an ordinary annuity. In this case, I'll start with the formula. The future value, the subscript there is time. The future value at time 5 is C times 1 with R to the T less 1 over R. So the future value at time 5 would get you 500. That's the amount per year. That's how I know it's an annuity. It's repetitive. It's a fixed amount for 5 years for finite time. So I have 1 with R, which is 1.08. What is the time 5 value? And we have 5 years, so my time there is 5. So the exponent is 5. Less 1 over 0.08. So if you do that correctly, you should get to $2,933.30. The other way to do this problem is to say on a timeline, this is time 0, that's today. From time 1, 2, all the way up through 5, you're receiving $500 per year. Now, if it doesn't specify when the cash flows start, always assume they start at the end of the period. Those are ordinary annuities. And notice this one doesn't say it, just says what is the time 5 value of a stream of cash flows, which will pay $500 per year for 5 years. That's by far the most common. So there's your payment, PMT. That's the fixed and finite portion of this equation. We have N as 5. We have payment as 500. And notice here, the present value we need to actually set is 0. And the way to think of that is there's no lump sum today. There's no starting balance today. We are just valuing these 5 cash flow streams, these 5 patterns. And we're going to compound those at the IY rate. And we're going to determine the future value. So that's just a summary of everything we're going to put in this row of buttons. So N is 5. So we'll go 5N. Our rate is 8. 8 IY. 500 payment. No starting balance. So 0 lump sum. Think of that as a single cash flow there for present value. There's nothing there. We're just valuing the 5 payments of 500 compounded at 8%. So we're going to compute future value. Ignore that negative. The way to think of that is if you were to maybe receive those 5 payments of 500 over the next 5 years, you as a loan would have to repay back $2,933.33. So 30 cents. So that's your answer there, $2,933.30. All right, now one of my favorite future value equations. This one you won't see in a whole lot of textbooks, but I always love to cover it because it's how I think about retirement. If you're saving for a future goal, such as retirement or even education, rather than thinking of saving a fixed amount per month or per year, think about increasing the amount you save. And you say, well, that's harder and harder. because of inflation or whatever. Well, that's fine. But if your salary's going up, then theoretically you should also be able to increase the amount you're saving. So that's why I like to include this one. And as just a reminder of that formula, the future value is C times 1 with R to the N or T less 1 with G to the T over R less G. Sometimes you see T for time and sometimes you see N for time. So the future value here is 40. You want to retire in 40 years with $1 million. So that's 1 million. And C is the amount of the first contribution that you have to make at the end of the period times 1 with R. So that's your compound rate, R, of 7.5%. And since we're using this in a formula, we have to move that decimal 2 places. So it'll be 0.075. When we combine it with 1, it's 1.075 to the power of time. This is 40. We're going to save each year starting next year, which is the same thing as saying starting at the end of the year. So that to the power of 40, less 1 with G, so 1.03 to the 40th over 0.075 less 0.03. Now, take a second just to think about how much you think you'd need to save every year in order to be a millionaire in 40 years. Just as a fun little exercise here before we actually do the math. Take a little guesstimate and see if you're close. So I've done this exercise in classrooms, and typically students will overestimate the amount they need to save in order to get $1 million, which is similar to saying they underestimate the effect of compounding over a long period of time. But this exponent of 40 is going to have a pretty dramatic effect. So what we're going to do is I'll show you the 1 million on this side. If you do all this correctly in terms of PEMDAS and order of operations and things, the answer you should get here in this term is $328.49.33. So I'll actually show you how I do this one. I will start with the 1.075 to get to an exponent in this calculator. You just use this y to the x button and then go 40 equals. So that figure, the 18, is the first term inside the hard bracket. So I'm going to save that number. And to do that, I'm going to go store 1. Then I'm going to calculate the value of the 103 to the 40th. So 1.03 y to the x 40 equals, that's the second term. So I'm going to save that and go store 2. Then I'm going to do the denominator, which is going to turn out to be 4.5%, but let's just go ahead and do it. 0.075 less 0.03 equals store 3. That's the third number I'm calculating. So now I'm going to put all those together inside the hard brackets, and that's recall 1, that's the first number, less recall 2, that's the second number, equals, that's the numerator in the hard brackets, and then divided by recall 3, the denominator we initially calculated. So that becomes the term inside the hard brackets. And now if you remember, to get to C, we have to divide both sides by this term. That's on our calculator. So 1 million divided by this. And actually the way I think of it is I'm going to take that number that's in my calculator, inverse it, write it out here so you can see what I do. Inverse, and then multiply it by 1 million. That is actually the same exact thing as just dividing both sides by that term. So however you like to think about it. The reason I like to do that is I don't like to round intermediate calculations. If you do enough math in finance, you realize if you're starting to round things with interest rates, with exponents of, sometimes 360 for mortgages, it does have a pretty wild effect. So we're going to take this inverse, which is just 1 over the x, that term, and then multiply by 1 million. And I know some of you say, well, I have a TI-84 or whatever, but if you're taking an 400 level finance course, I have a large population of students that will end up getting their CFA or their CFP. So the faster you are with a financial calculator, the better some of those standardized tests become for you, especially if you're looking for some kind of investment credential. So go back to that number, maybe you estimated in your mind. This is the amount of the first contribution in the first year is $3,000. So after the first year, you can save 3% more, and every year you're going to increase that contribution by 3%. Perhaps maybe you estimate your salary to grow comfortably by 3%, so you can increase your savings by 3%. So when I ask students this in class, a lot of them will think this number is a lot higher, maybe $5,000 or $10,000 a year. Now, maybe you say $1 million is not enough for retirement, so perhaps double this number, your future value will then double. So I know I use a lot of financial calculator. There's multiple ways to do these. We've used the formula for all of them. Excel's a very powerful tool as well. So if you are going to get a role in finance, most of the time you're going to end up using Excel for these calculations. But I think if you build your intuition with the formula, then Excel becomes much easier. We get a lot of students that end up getting roles. And some of the feedback we get from employers is that we wish they understood kind of the DCF math a little bit better. So hopefully this helped you out a little bit. The one thing I want you to think of is there's not just one way to solve a problem. And this is one of my favorite quotes from one of my favorite movies. As you will find, there's a number of solutions for any given problem. So if you can solve it one way, try to think through some other ways. All right, on to my favorite football player, Jim Kelly. 1986, he signed with the Buffalo Bills. And what I thought was cool about this article is he was at the time the highest paid NFL player in history when he signed a 5-year, $8 million contract. So if you're a sports fan, you kind of know how these contracts work. They say it's an $8 million contract, but that's the total amount they'll end up paying you over the 5 years. Now, if you're in finance, you will say, well, that's not really $8 million if you were to calculate its present value. So that's what we're going to do. We're going to calculate the present value of these payments. The first thing we're going to do is we're going to assume that Jim Kelly will receive this 8 million spread evenly over 5 years. So we'll just take 8 million divided by 5. So 8 million divided by 5 years will come out to 1.6 million per year. I know some of you are thinking that's not very much money, but I'd be happy to take it. So if the discount rate is 6%, let's just outline the cash flows. In 1986, that's time 0 for us. That's when Jim signs the contract. And then in the first year, 1987, time 1, he'll receive 1.6 million. And again, there's the 1.6. That's your payment. So you could think of it as your payment. PMT on your financial calculator is $1.6 million. The future value is 0 in this case. There's no additional lump sum out there. Your discount rate, your IY is 6, your time is 5, and you could compute for your present value and you would get this 6.74 million. So let's just do that just for fun. So 1.6 million, 1600000 is your payment. There's no future value. Just think of that as there's no additional lump sum at the end of the period. There's just those 5 payments. Your discount rate is 6, and we're going to compute for the present value. So that is the 6.74 million right there. I just rounded a little bit. Now, one thing to think of is if Jim was offered a choice between would you like your 8 million spread evenly over the next 5 years, or would you like a lump sum of 6.74 million? Jim is indifferent at this point. And this point of indifference, the way I like to think about it is in terms of an equation. So the present value today is just the 8 million over the 5 years times the 1 less 1 over 1 with R, the fifth, over 0.06. So at that point, they have the same value. He's indifferent between the single lump sum of this amount or the annuity payment spread. But if Jim was offered the same deal of the 6.7 million today or 8 million spread across 5 years, and Jim can actually earn 10%. If you do the math on that one, let's just do it for fun. Let's say that's the value of the lump sum. That's your present value. And he can earn 10% interest rate. And again, over 5 years. We already had the 1.6 in there. We can compute the future value. He's going to be left with an extra million. So the point of this exercise here is to say, if you can get the lump sum, but you can compound higher than the discount rate initially valued, there's going to be an additional cash flow left over. Because if he can only earn 6% and he took the choice of the 6.7 million, well, he could compound that amount for 1 year, make himself a payment, and then what's left, compound that for 1 year, make himself a payment, compound what's left, make the payment, compound what's left, make a payment, compound what's left, make a payment. What's left is a future value, a balance of 0, because that initial present value we looked at can only make 5 payments of 1.6 million. There will be no balance left over. However, if he can compound at a rate greater than 6%, there will be some money left over. So if Jim can compound at 6% or higher, we'd recommend he take the lump sum. Now that's a little tricky to think about conceptually, but feel free to go back and play that again. All right, let's start with part 2, interest rates. And interest rates can be confusing. So what I'd recommend you do is study these definitions and use them to help you think through them. An annual percentage rate, or an APR, is an interest rate charged per period times the number of periods per year. You'll see this rate. It's quoted by law. You'll see it in a lot of contracts where people discuss an APR. So an APR is just the number of compounding periods in a year times a periodic rate, R over M. And we use this R over M a lot when we do discounting and compounding. This is often called the rate per period or the periodic rate. So the effective annual rate is the rate your money actually compounds. It's the rate you'll actually earn. It's not the same thing as an APR. APR gets quoted, but the effective rate is the rate you'll actually earn. So it's the right rate to think about if you're thinking about a portfolio's value over a number of periods. Let's take a look, and when we will use some examples here with an APR of 10%. So all of these scenarios have an APR of 10%. If the APR is 10 and there's annual compounding, your effective rate is going to be the same thing. However, if you're compounding more frequently at 1/2 the rate, the effective rate will increase. So the math for an EAR, or an effective annual yield, or an annual percentage yield, is the interest rate expressed as if there was only one compounding per year. It's the actual rate paid or received after accounting for the compounding. So what did I do to get this semi-annual one? So in the semi-annual, I took this effective annual rate equation. I said 1 with the APR of 10%, 1 plus 10% over semi-annual. That's 2 semi-annual periods in a year to the power of 2 less 1. That will come to 10.25%. So, okay, what does that mean? I like to think of these also on a timeline. Let me just rewrite this portion here. That's 1 with 5%, right? Squared. So the way to think of this is, if there's compounding once in a year, if this is time 0 today and this is 1 year from now, if you're starting with $100 and there's only one compounding, you'll be left with 10%, 110. So your effective annual rate will imply, if you invested 100 and now you're left with 110, your effective annual rate is 10%. But if you get to compound, which we saw here, you're going to compound twice, 2 compoundings at 1/2 of the rate, right? 10 over 2. You're going to essentially start with 100, and then in 6 months, you're going to stack some interest at 105. And then 6 months later, you will have 110.25. Well, where'd this quarter come from? Well, it's the interest earned on interest. And the reason the effective annual rate is now higher than if there was compounding once in a year is because you started earning interest on interest faster. So that's why the effective annual rate will differ than your annual percentage rate. Because remember, the effective annual rate is the actual rate paid or received after accounting for compounding that occurs during the year. It is also the interest rate expressed as if there was compounding once per year. So what does that second definition mean that I read? Well, you started with 100 and you're left with now 110.25. That means effectively you've compounded at 10.25% despite being quoted an annual percentage rate of 10%. I know this is tricky. I know this is a little confusing, but take some time to think about it. Let's do another one. Let's do a quarterly basis. If we start with $100, then we're going to let's first find the effective annual rate and then we'll check our work here. That's 10% over 4 because there's 4 quarters in a year. So that's 10% over 4 with 1 to the power of 4 less 1. So let's just check our work here. So that's spot 1 over 4 with 1 equals y to the x 4 equals, and then less 1 equals. So that'll be 1038. Some of you may not be surprised to see that that's higher than the 10.25. So we still have an APR of 10% quoted by law. But why does this change? Well, in 1 quarter, we're going to start getting interest, right? So we're going to take the 10%. So we have spot 1 divided by 4. We're going to start earning 2.5% per period. So that's 102.5. So we'll have 100 times 1.025. That's your balance after 1 quarter. Then again, times 1.025. In 6 months, you'll now have 105.0625. And then again, times 1.025. Now you'll have 107.69. And then again, times 1.025. Now you'll have 110.38. And that's the 1038 you see up there. So your effective annual rate implied here is 1038%. Now, the way to think of that again, the effective rate is the one rate as if there was compounding once per year. You started with 100, you left with 110.38. That implies an effective annual rate of 1038%, despite only being quoted an APR of 10%. So the point is, as the compounding periods per year increase, the effective annual rate increases. And just think of that as you start earning interest on interest faster. And that's what we want to do. We want that interest compounding. So here it is. I've put all of these into common compounding frequencies, such as annual, semi-annual, quarterly, monthly, weekly, daily, all the way up to continuous. And if you get to continuous, it reaches some limit, which is Euler's E. So the effective annual rate is Euler's E to the compound rate less 1. So to do that on your financial calculator, you would just take spot 1, second log natural, which is actually here, e to the x. And I have spot 1, second e to the x. 110.51 minus 1 is an effective rate of about 10.52. So all of these scenarios start with the same annual percentage rate, but they effectively compound much differently. If you're more of a visual learner, perhaps you can see this easier, is an annual will have the same effective annual rate, but as the compounding periods per year increase, the effective annual rate increases, and then it reaches some limit. All right, so if you do get a question where there are periods other than a year's with the interest rates, we have to go back to that periodic rate and then be consistent. So remember that valuation is all about 3 things: timing, risk, and magnitude of cash flows. So if you get cash flows occurring on a monthly basis, we need to consider time in months, risk, or our interest rate is a rate per month, and then magnitude, those cash flows have to occur monthly. Timing, risk, magnitude all now need to be consistently monthly. So I'll give you APRs if you'll give me APRs. This is the rate we typically see in finance. Again, we saw that in the definition that it's required by law to give this one. So just be consistent. So if, for example, if you get a question that says something like R%, the R is your APR, and then it says compounded semi-annually. This is just telling you how that start stacking interest, or when it starts. In this case, it'll accrue interest every 6 months. So if you get a question that says 10% compounded semi-annually, you need to take that APR of 10%, divide by 2, and it's really 5% per semi-annual period. And then the cash flows need to be consistently measured on a semi-annual basis, such as bonds. And then you need to measure time in semi-annual periods as well. So these three things need to be consistent. That rate, we consider the risk, the magnitude, and then time for a number of semi-annual periods. I think it'll be easier if we do this with a little example. So let's start with a new computer system. The store allows you to make monthly payments. Now that's a very key word when you get these questions, is what payment frequency. So we have the timing here now is monthly. So we have to look at three things just by reading that one word: timing, risk, and magnitude are all now consistently need to be measured in months. So if we do this in a financial calculator, if we have a loan payment of 2 years, the time is not 2 years. The time we need to value is actually 24 months. And I know you're saying, well, Chauncey, that is the same thing, but we need to consider the time accurately and we need to measure it in months. So your rate is 16.9 with monthly compounding. That 16.9 is an APR, an annual percentage rate. So you need to take the 16.9 over 2. That becomes a rate per month divided by 12, 16.9 over 12. Present value, that's the value of the system. 3,500. We're going to pay that loan balance off to a future balance of 0. So let's do 24 and 16.9 over 12 is your IY, 3,500 present value, 0 future value, and then compute payment. You would need to pay 172.88, and you received the value, positive value of $3,500 system. Now you need to pay outflow, negative sign, $172.88 per month to pay off the system. It's the same thing you get formulaically. Again, just be careful with timing, risk, and magnitude. All of those are monthly. Let's look at the next one. You're saving $50 a month starting next month. That's an ordinary annuity. Same thing as saying starting at the end of the month. You're depositing 50 a month into an account that has an APR of 9% with monthly compounding. So again, when you see these months in here, be very, very careful. Timing, risk, and magnitude are all now monthly. So the payment is 50. The rate is 9 over 12 because it's monthly, 12 months in a year. How much will you have in 35 years? So your time is just 35 times 12. And your present value is 0. There's no starting lump sum, or you could just think of you're valuing these payments of 420 months of $50 a month. So there's no initial amount. So let's do that. Let's do the 35 times 12 for 420. Time and risk 9 over 12, our rate, our compound rate. 3/4 IY, 0 PV, 50 PMT, and then compute future value. Wow, $50 a month over a long period of time. That's quite a bit of cash right there. $147,089.22. So that is the same thing you'd get if you did this formulaically. All right, let's take a look. Here's another example. You're welcome to read this. I like this choice, as my finance professor showed us this one when I was an undergrad. He said, you notice your coworkers go out to lunch every day and order fast food. You're trying to save more money and eat healthier, so you decide to bring a sandwich or a salad from home 1 extra day per week. You conservatively estimate you can save $20 per month by adopting this habit. How much extra cash will you have after 30 years? if you can invest your savings at an APR of 10%. So you assume you invest the first $20 1 month from now. That's time one. That's an ordinary annuity. The second 2 months from now, time two, etc. So you're going to do this for 360 months. That choice will actually leave you $45,000 richer by the time you retire. So your future value would be 45,000. So all this is saving $20 per month. So your payment was 20, your rate was 10 over 12, and your present value was 0. Your time was 30 times 12. And this is an amount, dollar per month. This was a rate per month. I like to write out these units just to make sure we didn't miss any. And this is number of months. And so we're going to compute that future value. Let me show you. So again, we're going to use this row of buttons. 20 is the annuity payment. 10 over 12 is your IY per period. 0 is your present value. And then 360 or 30 times 12, n number of months, and then compute your future value. $45,209.76. That's quite a savings there. And you're eating healthier, it sounds like in the question. So that's a nice one to look at. All right, let's look at another example here. You have a choice here of an investment banking firm of Dewey, Cheatham, and Howe. You're offered two different salary arrangements, $68,000 per year for 2 years. The first one here. Or $57,000 per year for the next 2 years. That includes a $13,000 signing bonus. So what's the value of each option today? This is a present value case. There's no future values here. There's no additional lump sum outside the salaries. It says in the question here that the salaries are paid in equal amounts at the end of each month. So for the first one, that's $68,000 per year over 12. That's a payment per month. So we need to look at a discount rate per month. So we need to take that 8 over 12 to get to a rate per month. And then time needs to be in months. So that's 2 years at 12 months in a year is 24 months. Just going to put the units right there. And notice we have 3 of them that are consistent. The magnitude, the risk, the time. And so we'll compute that present value and we'll compare it to the second option. So the second option, again, future value of 0. There's no golden parachute when you leave this firm or anything like that. That's 57,000 over 12 at a rate, again, still of 8/12. And time is 24 still. And we're going to compare that present value. That would be the present value of the salary stream, that annuity, but you also get a 13,000 signing bonus. So we have to add that amount to get to the total value of that choice. So 0, future value, 68,000 over 12. That's your monthly payment, not too shabby. 8 over 12 is your IY. 2 times 12 is 24. Make sure you hit equals, because if you were to hit time right now, it would enter in as 12. So equals 24, end periods, and then compute your present value. That, ignore this negative here, the value of this choice, the present value of that salary is $125,293.08. So that's the first choice value. The first choice, let's look at the second one. All we have to change is the 57,000 over 12 for the payment and then compute that present value. The other will stay in there. Drop that negative. That $105,025 is just the value of the salary, does not include the sign-on bonus of 13. So we're going to add the 13,000 to that. And that choice is only worth $118,025.08. Now, maybe if you got that choice, what I'd recommend if they offered you the second choice, is actually ask if they could put that onto the salary instead. So often I think you'll find that employers would do that. So just we'll quickly reconsider that example. If you had the 57,000 plus the 13,000 as an annuity, as opposed to a single cash flow, you're going to look at 70,000 per year over 12. That's 5,800 per month payment, and then compute that present value. This would now be a better choice. So if you are able to convert this single cash flow into an annuity, then it would be a better deal. And hopefully you're building some of that intuition, saying like, yes, I'd rather just get paid that for a couple times rather than just once. All right, you have parents that I didn't have. If they just gave you a BMW M6, but you said, "Hey, that's not the kind of car I want." Instead, you sell the car for 61,000, spend 11,000 on a used Corolla, and then use the remaining 50,000 as a down payment for a house. So, wow, look at you. You're making some really good financial choices here early on in your career. The bank offers you a 30-year loan with equal monthly payments, interest rate of 6, and they require a 20% down payment. So what would this look like? How much can you borrow and what will the loan payment be? So first thing you need to do is determine how much a house you can afford. So first thing is to say $50,000 is 20% of what? So 50,000 equals 20% of, we'll just say, house or value. We'll just of some value. So the value is, take the 50,000 over spot 2, and you say $250,000 for a house. Now you're going to put 50,000 down, remember. So the value of the home is 250,000. That's not how much you're borrowing it. When you say you're putting an amount down or a down payment for a house, that means you're lowering your mortgage by that amount. So the amount you borrow is actually going to be the 250,000 house minus the 50,000 we say down, which makes your mortgage, or the amount you borrow for a home, is only 200,000. Gotta love a job where you say only 200,000, don't you? That's the answer to the first question. How much can you borrow? You can borrow 200,000. So that's your present value on your home. So your present value is 200,000. You're going to pay that loan balance off to a future value of 0. Your discount rate is 6 over 12. That's going to be a rate per month. And time is going to be 30 years times 12 months in a year for 360 months. And then we're going to solve for a payment amount, which will come out as $1 per month. So those three things of timing, risk, and magnitude are now all consistently measured on a monthly basis. So 200,000 is your present value, 0 is your future value. Pay that loan off to 0. 6 over 12 rate per month of a half, IY, 360 or 30 times 12, n number of monthly periods, and then compute for a payment. You'd have to pay $11.99 per month. So $1,199.10 per month. Kind of neat. Kind of neat idea there to sell a car, get by with a used one, and just start buying a house. And who knows, maybe you can rent that out, make some additional income. Kind of fun doing this. I like these examples where we actually get to apply it. So thank you, Lorenzo, for that example. Now we're going to look at loans, and often in loans you'll see car loans and mortgage loans. So you see these applied a lot in personal finance, but Debt financing is very, very common even in corporate finance. So it's nice to know how annuities work. They're amortized. You're getting annually quoted rates. Let's take a look at a car here. So let's do some formula. We're doing a lot of financial calculators lately. So your present value of this car is $26,000. Let's use the annuity formula. We're looking for a monthly payment. So C times 1 over 1 C times 1 less 1 over 1 with R. So 1 with R is 1 plus spot 0, 6 over 12. And this is a 4-year. So your time, your exponent here is going to be 4 times 12. And your rate is spot 0.6 over 12. Your first payment is C. That's what you're looking for. Your present value is 26,000. So if you did this correctly, the piece you should be looking for is C. That should come out to $610.61 per month. Now, if you don't really appreciate the formula that much, your present value is the value of the car. You're going to pay that off to 0, or you could think there's no additional payment you have to make at the end. It's just the amount. It's just the 48 monthly payments you're looking for. So we're looking for a payment per month here. Your discount rate is 6 over 12, 1/2 rate per month. And then time is 4 times 12 for 48 months. So let's just check timing, risk, magnitude. All of those are on a monthly basis, so we are good to go. Common mistakes for students is to forget to change one of those and then see a distracting choice as an option on an exam. So pro tip, 26,000 present value with 12 or 1/2 IY per month, and then 48 end months with 0 future value, and compute for your payment. 610 payment and 61 cents. So 610.61, that would be the same thing as if you did the formula. 610.61 per month. Okay. Let's take a look now on loans, because when you take out a loan, the cost of borrowing is interest. So if you're looking at the total amount of interest you pay on a mortgage or on a car loan, you take your total payments and then deduct the change in principal. All right, here's an example. Let's take a look at this 30-year loan. Before we look at some of the charts and graphs on it, let's just do some of the math for ourselves. The present value of this home, I just double check, that was a $300,000 home. Yep, so your present value is 300,000. Your future value is 0. You're going to pay that off to 0. We're looking for the amount per month in monthly payment. Your rate is 6 over 12 rate per month. And your time is 30 years times 12 months in a year is 360 months. So timing, risk, and magnitude are all there, consistently measured on a monthly basis. So all that looks correct. So let's do the math. 360 months at 1/2 rate with no future value and a $300,000 home for a present value, and then we'll compute that payment. That will be a payment of $1798.65. Now let's take a look at what this implies. Some charts and graphs here. This is an amortization table, and all an amortization table tells you is how much interest and principal to pay each period. So there's a couple things you notice. This amortization table has been truncated. I've just shown you the first 3 months, the middle 3 months, and the last 3 months. So this will actually be much longer than this if you saw the whole thing. Notice the beginning balance starting in month 1. That is your present value. That present value is 300,000. It's going to have a future value of 0. So we typed that in our financial calculator and we solved for a payment. That's your annuity, fixed and finite cash flow. So that's the payment right there. Each payment is equal to interest and principal. That means part of your payment goes towards interest and part goes towards principal. Early on in a mortgage, month 1, 2, 3, for example, most of that payment goes towards interest and very little goes towards principal. Principal refers to how much you owe still. So very little of that initial payment will go towards principal. And how do we get that interest? Well, you took out a loan for 300,000 and then it accrued interest for a month. And how much interest did it accrue? Well, it was a $300,000 home and you had a 6% APR, which is 0.06 over 12 as a rate per month. So if we took 0.06 over 12, your monthly rate of 0.5% times 300,000 balance is 1,500 in interest. So how much was principal? Well, you take your payment of $1,798 and deduct the interest. The remainder is principal. So 298. That is the amount by which your loan balance will decrease. So deduct that from your beginning period loan balance of 300,000. And you'll see the ending loan balance of 299,701. That ending loan balance in month 1 becomes the beginning balance in month 2, and so on. The other way to think of these balances is these balances are the present value of the remaining payments. So when you take the present value of, excuse me, when you take the present value of 360 of these payments, you'll find that the present value is 300,000. You could think of that also as stripping out the interest effect of those and just adding up the principal remaining of those payments. So let's take a look and just double check we can do that. So if you just look, we just compute that present value, we get 300,000. Now, if we say we made one payment already, well, now there's 359 payments remaining. Let's compute that present value. That's the present value of the remaining 159 payments. That means we've already paid that first one. And then let's say after we've done that one, we have 358 payments remaining. So time is now 358, and we'll compute that present value. So this 299,401 represents the present value of these payments. So we're just going to take out the interest effect of those. So here it is graphed again. Notice this chart has the same height for each payment, payments 1, 2, and 3. And for the last 3, they have the same height. But what I wanted to show you is the proportion of each that goes towards interest and principal. So initially, those first payments are very high in interest and very little in principal. But then over time, the last 3 are mostly principal and low interest. So don't get that mixed up with each other. Initially, those early payments have high interest. Just what I've done here is I've graphed all these together, and then this was principal portion. So this, let's take this middle one, for example. The vast majority of this, it looks like somewhere around here of 180. So even halfway through, most of your payment is going towards interest. And still a fraction is going towards interest. So if you forget which one's which, early on you pay high interest and then later on you pay more principal. But think of it as class. Perhaps early on in class your interest is high, and as it progresses it just goes down. Not in this class, I hope. Okay, let's take another look at this same loan. What's the remaining loan balance after your 12th payment? Now, I've seen a couple creative ways to solve this one. The one I like to do is I'm computing for a new present value. Future balance is 0. I'm going to leave that payment as $1,798.65 and take the rate, keep the rate the same at 6 and at 1/2, and then time now is 360 minus 12 after the 12th payment. That means I have 348 remaining. So let's just take, let's go back and put the calculator back at 360 time, compute for my present value. Okay, that's all set. So let's take 360 less 12, and that's the 348 remaining payments, and I'll compute for that present value. the present value is $296,315.96. So another way to solve this one, so the way I viewed this in this case is to say, if this is today and this is time 1 through 12, I've already made these payments at time 1 through 12. And now I'm looking at the 13th through the 360th inclusive payments. So there's time there of 348 months right there. So I'm taking the present value of my remaining payments and saying that's my principal. The other way you could view this, equally accurate, is to say, hang on a second, I'm making these payments, right? Those are cash outflows, and I have a positive balance of my home of 300. So you could view this as I'm making these payments. If I start in 1 month, I'm making this payment of $1,798.65, and I have a positive. I started with a positive $300,000 present value, and this goes for 12 periods, and compute for a new future value. So that balance at the future at time 12 is going to equal the same thing we just calculated. So let's just now just change our time to 12 and keep everything else in there and compute for a future. Oh, sorry, here. Let's go back to our initial base case here of 300,000 present value, 360 end months at 6/12 IY. That's our base case of 1798, right? So now we'll just change time to 12 and then compute for our future value. That's still the 196. So all I did there was, compared to the example above, we just changed n to 12 and we solved for our new future value. So feel free to use either of those approaches. Notice they'll get you the same exact answer either way you do it. How much interest is paid over the life of the mortgage? So we have to go back to this total interest and first look at the total payments. So total interest equals total payments minus delta, or change in principal. So total interest are your total payments of 360 times compute for your payment. This payment times 360. That was 1798.65 minus a change in principal. You'll pay it off to 0. So your change in principal is 300,000. So your total interest is the first part. You make payments of $647,514.57 minus principal of 300,000 if you pay the loan off. So the part that's interest, or total interest, is $347,514.57. Now, don't get me wrong. I'm not trying to say mortgages are bad or anything. I'm just saying they can be dangerous, but it is nice to know what kind of leverage you're working with before you make some more decisions. So let's look at another one here. Lease and buy a car. This is probably the trickiest one in the whole question. You're looking at a new car, so should you buy or lease the car? I like to set this one up formulaically. As it gets more complicated, it just makes it a little bit more straightforward for me to see it this way. You're going to calculate the present value of each cost. So we'll find the present value today of leasing the vehicle. So the present value today of leasing the vehicle includes a single cash flow plus an annuity. So C times 1 less 1 over 1 with R to the T over R. So if I did this correctly, it's a 99 single cash flow plus 499 times 1 less 1 over 1 with R, which is 1 plus spot 06 over 12 to the power of 36. That's 3 times 12 over spot 06 over 12. So if you did this correctly, the present value today of the lease is going to be $16,501.64. And then the second case here, I'll set up the formula of the purchase. Present value today of the purchase is a single cash flow today of the car minus the future value of being able to sell it. So think of that as that reduces the cost of the car today because you get this cash flow later, 1 with R to the T. So the single cash flow is $35,000 cost today, but you get to sell it, so that'll reduce your cost if you think about it that way. 23,000 over 1 with R, so 1 with 6 over 12 to the 36. The present value today of the purchase. Take some time to pause this video and read through this question. This is the trickiest one there, so don't just take my word for it. It's $15,780.17. That has a lower cost, so we should buy the car. So common financial decision choice here, lease or buy. Now, at what point would you be indifferent between the two? So the trick to this one is you just need to set the two equal to each other. So to say, what's present value today of the lease makes it equal to the present value today of the purchase. So to do that, we already know the value of the lease today. We solved that initially, $16,501.64. Equal to the present value of a purchase. Well, the purchase included a cost of $35,000 today that was reduced by being able to resell the vehicle. So the resale price is what we're looking for. So I'll just call that resale. That's the piece in the numerator up here. The only piece we're changing in this new equation is that 23,000, and we're just solving for X, or what I call resale. That's 1 with R, so that's 1 with spot 0.6 over 12. That's your rate per month to 36 months. Oh dear. The computer's dying. Let's see here. So if you did this correctly, your resale price is going to be $22,136.63. So thank you so much. The computer's about to die. It has been a pleasure.